Great, thanks, Carly. So I was asked to talk about the surfaces of dwarf planets or trans-Neptunian worlds. I'll use those terms interchangeably. Um, there are three that have been observed by spacecraft so far: Triton, Pluto, and Charon. And so their pictures are shown here. What I'll do is start by talking about them kind of in a comparative context and sort of what we can extract and use to predict about surfaces that have not yet been explored. And so then I'll use that as context to talk about unexplored trans-Neptunian worlds, and I'll focus specifically on Eris and Haumea, try and make some predictions. Okay, so starting off with Triton, it's been mentioned a few times in this workshop, but not talked about yet in detail. So 5 surface characteristics of Triton, sort of observational characteristics: albedo, color, composition, topography, and age. In all 5 of these characteristics, it can be said that Triton is approximately uniform, not a lot of variation across the surface in this regard in comparison to other similar worlds. So the albedo is, again, approximately uniform and quite high. About 80% of all the solar energy is either reflected or scattered back into space. When we make a map of Triton, of course, we stretch it. And so, in our eye, we're used to seeing color variations. But again, the color is actually relatively uniform and mostly neutral of Triton. Triton does have a super rich inventory of both volatiles and refractory materials. However, one important thing about Triton's composition is that we don't really have a good sense for where those materials are located. And that really, we'll see, strongly hinders interpreting the landforms. That's different from most other places. And that's relatively straightforward to remedy, of course. A capable near-infrared spectrometer on a spacecraft would really fix that. The topography is generally low amplitude, less than a kilometer on areas that were constrained by Voyager 2. And then Triton, there's variation in age across the surface, but all of the surfaces are very young. In a global sense, Triton is the youngest of all the icy worlds. This is a very young, active world. Okay, so then switching from that to the Triton landforms, the geology and geomorphology, it's the exact opposite, surprisingly. So whereas those features are all relatively uniform, Triton has this huge diversity of geology. And that diversity includes both endogenic, and by that I mean primarily and internally powered, and exogenic, primarily externally derived terrains. And again, because we don't know exactly where what composition corresponds to which landforms, there's not a really strong sense in literature of which terrains are endogenic and which are exogenic, but there is doubtlessly both. And so on the endogenic case, there's tectonic features such as ridges that are almost certainly endogenic, and there must be some amount of sublimation and condensation. There's also an atmosphere that is blowing features, so the fans that are in the southern hemisphere, those are windblown features. This eruption plume is also windblown. And then likely other exogenic features as well. So in addition to having diverse surface morphologies, Triton also has its own unique morphologies, and probably the most dramatic of those is the cantaloupe terrain. It's this huge province on Triton, and there's really no direct analogy for it that I'm aware of in the solar system. There's some resemblance to Sputnik Planitia, but definitely a very different character here. The leading hypothesis for that is that it's due to diapirism, but there are published other hypotheses as well, exogenic. And then in addition to being diverse and unique, so I'm going to, the title had this diverse, unique, and active. So I'm going to talk about those 3 terms a lot throughout this presentation. Triton also has surfaces or landforms that were active literally on the tens of minutes to hour-long time scales between Voyager 2 images. There was, for example, multiple plumes that were seen to be erupting on Triton, that this long trailing cloud and images less than 45 minutes apart, separated as Voyager 2 flew by, you could see that cloud changing, indicating, the eruption is not puffing, but it's kind of just, variation in cloud and time as it's erupting. So Triton has this very diverse, unique, and active surface. Okay, so just diving in a little bit more into the plumes, there are many hypotheses that have been published for them. both eruption and non-eruption. Eruption are generally favored. That's because these plumes generally rise straight up, and that implies a relatively high speed, which is most easily generated by an eruption. But the eruptions could be exogenic, a sort of solid state greenhouse. Solar driven process has been proposed and favored for a long time. It could also be maybe more Enceladus style, coming from a deeper reservoir. And then there's this model that's not as well known, but the idea is that there's internal heat and there's a thick layer of nitrogen ice that insulates that and possibly even allows basal melting, perhaps somewhat like Orkan and Alan were talking about earlier this week. So I've looked carefully at all these three hypotheses. I would say that they all have pros and cons, and we really don't have a strong discriminator between them at this point. However, in 2022, we published a set of 5 tests that could very confidently distinguish between these hypotheses and are relatively straightforward to implement, you know, a sort of typical spacecraft architecture, flyby, multi-flyby sort of thing with a camera and near-infrared spectrometer. Could go through these tests that we just kind of have this logic. I won't go through the tests, but we published this, and this could, these tests are, first of all, independent of each other, but complementary. And again, they could definitely distinguish between these hypotheses. RIP, maybe it's more appropriate. Okay, Pluto, on the other hand, it really could not be more different from Triton, given the similarities. In terms of its bulk properties, it's very similar, but the surface is astoundingly different. So 10 years on, that is still, to me, one of the most amazing things about the flyby is that these worlds are just so different from each other. And in these 5 characteristics that I talked about for Triton, all being very uniform, Pluto is the exact opposite. It is extreme in its variability. The albedo varies from 0.1 to 0.9, which for large terrains like 1,000-kilometer scale terrains, there's nowhere else in the solar system that has this big a difference. And so it's really extreme in that regard. And then likewise for color, terrains vary from a tad bluish to extremely red. And the New Horizons saw the ratios vary by more than a factor of 2. So those variations in color and albedo are correlated, not perfectly, but there's definitely a relation between them. And then Pluto has its own, rich array of materials. And on Pluto, we have the advantage of having a better sense of how those materials are distributed with the types of landforms. Pluto's topography, it has large variations. It's not as extreme in this regard, but a total relief of about 11 kilometers. And so plenty of topography on Pluto, especially in comparison to Triton. And then the age, Pluto's terrains vary from, literally resurfacing as we speak to probably dating back to the epoch of formation, although give or take a factor of 2, given Kelsey's talk yesterday. So very strong variations on Pluto in these surface characteristics. Okay, so just diving a little bit more into the albedo. This is a map of the bolometric hemispherical albedo. This is, in a physics textbook, when you're doing introductory physics, this is the albedo. It's the energy that is not absorbed at the surface. And so this is a map of that on Pluto. And I've already emphasized that there's this huge variation in dark and bright. But what I also want to say is that it is actually extremely spatially sharp, which is also very rare in the solar system. Literally, pretty much in New Horizons images, there is 1 pixel that is very, very dark, and the pixel right next to it can be exceedingly bright. And that is something that is, first of all, rare, and second of all, I think has to be, the surface has to be working hard to preserve that, otherwise space will undo it. So Pluto, just like Triton, given all those changes, all those variations in the surface, you might expect that it has diverse landforms, and indeed it does. And Pluto has both endogenic and exogenic landforms, just like Triton. However, it's worth pointing out that there's actually very little overlap in terms of at least the character of these landforms between Triton and Pluto. So although they're both very diverse and have a ton of different terrains, they actually have almost no terrains that are directly analogous. Craters, of course, and some amount of sublimation, perhaps, are the two that come to mind. So some examples of endogenic, we have tectonism, of course. We have cryovolcanic features, and then there is the Sputnik planitia convective resurfacing. Exogenic, we have sublimation and condensation going on Sputnik, glacial flow, bladed terrain, and then the atmosphere seems to be really depositing a lot of material onto the surface as well, and processed material. So Pluto is definitely diverse, definitely different from Triton in its diversity. Just like Triton, however, it also has features that are really unique to Pluto. So one is Sputnik planitia, the convective resurfacing, again, maybe some analogy to that unique cantaloupe terrain on Triton, but this one is probably much more volatile rich and also certainly different in its appearance. Cryovolcanism is seen in other places and hypothesized in plenty of places, but not really at all with this kind of huge edifice type character. And so I would say that's unique. And then the bladed terrain, okay, it's analogous to penitentes perhaps on glaciers on Earth, but the scale is just orders of magnitude different. And so it really is, I would say, unique, and of course, different chemistry as well. And then Pluto, diverse, unique, and active. Pluto is almost certainly active in today. The crater retention ages are basically zero on some of these terrains, including Sputnik planitia, active both in an endogenic and exogenic sense. And then glaciers is another one that comes to mind for activity. So it's worth saying that, however, although Pluto is without a doubt active today, Triton also is. Interestingly, we saw changes in the images from Voyager 2 at Triton. We did not see that with New Horizons at Pluto. And I know because I looked at essentially every possible image and looked for changes. And we did not find any that were indicating there's a time varying phenomenon. So we published sort of constraints on what the temporal changes were not seen as a function of spatial scale and the time interval. Those two generally trade off with each other because of the nature of the flyby. Not going to get into it, but I think this difference between Triton and Pluto is not a coincidence of timing or location. I think that those plumes that are on Triton are actually probably not occurring on Pluto anytime. And the reason for that is primarily because on Triton we see a lot of evidence for past plumes and very little for that on Pluto. And so it's not just probably a timing effect, but there's something more that's different between them. Okay, so just going a little bit more on that, there are not temporal changes that were seen on Pluto, but there were some extremely fascinating, I think, features that appear to change. And so they're shown here. There's 3 of them indicated by red arrows that are dark on their extremely bright background. And then in multiple images taken just a few hours later, those features are either not apparent or barely apparent. They're basically invisible. And then again, just a few hours later, they're now bright features. And so if you were, say, blinking like I did between these 2 images, just about jumped out of my seat, thought I found the plumes on Pluto, but quickly learned that this is probably not a time interval effect, but actually a change in the lighting conditions. In particular, this parameter called the solar phase angle, which is the sun surface spacecraft angle. And so in a paper that was just recently accepted, we showed that this is consistent with a surface effect, or actually it could be a low altitude cloud. And basically what's going on is that something on the surface is causing this particular area to scatter its photons more forward. And so that's why they appear bright at high phase angle and dark at low phase angle. And a cloud is very interesting, but it's not ruled out, but we actually prefer that this is a surface effect, because they do seem, not these particular ones, but others that are like it, appear to kind of follow the surrounding surface. And so they're probably on the actual surface. Okay, so the last of the sort of explored trans-Neptunian worlds, if you will, is Charon. This is a very large world dwarf planet in its own right. It's not just a moon of Pluto, but if it was out in the Trans-Neptunian region, this would be one of the largest of the objects out there in its own right. And it's kind of intermediate between Triton and Pluto in the sense that Triton is uniform, Pluto is extremely variable. Charon is longitudinally uniform, but has this latitudinal variation that was talked about yesterday, in particular the dark red pole. So it's dark and it's red, so it has an albedo and a color variation. But otherwise, the albedo and color are generally longitudinally uniform. The albedo is much lower than Triton, but actually still quite high compared to most TNOs, trans-Neptunian objects. And it's relatively neutral aside from the red polar area. So Charon, of course, is different from Pluto and Triton in that it does not have any high abundance of surface volatiles, but as Sylvia talked about yesterday, lots and lots of different refractory materials on Charon's surface. Charon's topography is extreme, total relief of 19 kilometers in the areas that were constrained, and so really, really extreme topography. And then the ages, so the northern hemisphere Ozterra is probably a little bit older than the southern Balkan Planitia, but they're generally both quite old. I have 4 billion years here because I, of course, put this together before Kelsey's talk yesterday. So 2 to 4 billion years old either way. Okay, Charon too has diverse surfaces, and so it's not anywhere near as diverse as Pluto or Triton, but it is still quite diverse compared to plenty of other icy worlds. And it does have both endogenic and exogenic landforms. And so in terms of diversity, of course, there's that diversity between the northern hemisphere and the southern hemisphere. And then endogenic, there is plenty of tectonism features that have shaped the surface in the past. And then exogenically, there's the hypothesis that was discussed that there's this polar unit that's sourced from methane on Pluto, so it has this external source, and so that would be exogenic surface. And then Charon also, this is not true of every world in the solar system, but it's true of all the worlds that we've explored in the trans-Neptunian region so far, that Charon also has unique and active surfaces. So there are many, many icy satellites of the giant planets, and not a single one of them has anything that resembles this red polar unit. And that's likely because, indeed, of this idea that that's sourced from Pluto. I think that's a strong argument in favor of that hypothesis. And that's unique to Charon as far as we've seen so far. And then if that's true, it's very likely active, although we don't see that activity going on today during the flyby. It's probably occurring at least once every Pluto orbit sort of effect. And so Charon too has its own unique and active features. And yesterday, Stuart pointed out 3 different features on Charon that are also unique to Charon, he said. So diverse, unique, and active is a recurring theme here. All right, so I'm going to switch now to talking about the unexplored trans-Neptunian areas. And it's worth saying, by the way, that there's still a lot of real estate on Triton, Pluto, and Charon that is not yet explored. And what I'm going to say also applies to those areas, but then in particular worlds as well, too. There's plenty of worlds that have not yet been explored at all with the spacecraft. So I think, the business of making predictions for these worlds is actually more challenging than it might be for other classes of worlds because of this great diversity. We've seen that there's this really strong variations both across worlds and also between worlds. And so I think that makes it hard to render specific or detailed predictions. But what we can do is to high confidence make some still, I think, very bold and exciting predictions about the surfaces of these worlds. And so I've listed 3 predictions here, each of which kind of has 2 subsets. So 6 different predictions that I think are all relatively confident and exciting. So namely that we're going to see diversity, again, across the surface and also between different worlds. And I think I strongly suspect there's still unique landforms out there that we have not yet seen at all, given that, every place we look, we're seeing new ones. And there will be endogenic and exogenic landscapes. It's a remarkable thing. One of the things that I learned from the New Horizons counter, that there is so little energy out there, but these species are so volatile that if you give them the slightest bit of energy internally or externally, they're going to move around. And then I think we'll see a variety of surface ages, and from the extremes to actively resurfacing to, basically dating right to the epoch of formation of the solar system. And so I think there's a lot more to be seen there. All right, so Eris, what I've done here is the same thing, these 5 surface characteristics. The ones in white are measured by telescopes. Observations have constrained them, at least partially. The green are predictions, either that I made as I was putting this talk together or that are published. So Eris's albedo is, first of all, extremely high. It's higher than any other transit-tuning object, basically anything in the solar system except Enceladus and its neighbors. Very, very high albedo. And it's approximately rotationally uniform. And the same is true of its color, that it's approximately uniform. In fact, it's so uniform that determining the rotational period has been quite a challenge, but as Ben said, appears to be now synchronous with its moon dysnomia. By the way, Eris was introduced briefly, but I meant to introduce it as well, that Eris is a lot like Triton and Pluto in its bulk characteristics. It has essentially the same radius as Pluto, within a few tens of kilometers, and roughly the same mass, slightly higher, somewhat higher density than both of them. It also has a much more eccentric orbit. It goes much further out from the sun than Triton or Pluto, but it does actually spend, for a significant part of its orbit, it can be considerably closer than Pluto at times as well. So a lot of analogies to Triton and Pluto. Its color is mostly neutral, or neutral-ish, and so it's a lot like Triton in terms of some of its, at least, global albedo and color properties. It's been talked about this morning. Noemi showed some of the plots that Triton, Eris, has nitrogen and methane volatiles. CO is not detected, but I would not be surprised to see it somewhere on the surface. And ethane is on Triton and Pluto as well, so it would be nice to see. And these refractory materials are not yet seen, but presumably are somewhere on the surface, or if not, are at least buried underneath the volatiles. So Eris's topography, there is a prediction that it's approximately uniform, again, more like Triton in that sense. And the argument goes that basically, in order for it to have had all the tidal dissipation it's had, then basically there's a warm lithosphere, and so it's not able to preserve topography very strongly. And then I, with others, have predicted that it's actually a very young surface. I think actually that Eris may be extremely active, perhaps the most active of any ICU world, given that very, very high albedo in combination with methane, which should want to produce dark red materials. And the fact that we really don't see that, I think, indicates the surface is refreshing itself ongoing. And it's not just volatile transport, but probably internal processes as well. So in terms of predictions for landforms, I think that there's undoubtedly volatile transport occurring on Eris. So that's the exogenic prediction. 2B, that the 2B is the prediction of exogenic landforms. And in particular, that volatile transport it almost certainly happens at some point in Eris's orbit, but may be ongoing today. And it may be different than on Triton or Pluto. The reason being that there is this extreme solar eccentricity, and it's also, if its spin pole is aligned to the orbit pole of its moon dysnomia, which is likely given the tidal effect that's occurred, then it would have a variation at subsolar latitude of 78 degrees. Pluto is more like 60, Triton is more like 50, and so it's even more extreme than them. And so I think that could result in maybe some unique, or at least probably variations latitudinally across its surface. And so probably diverse volatile transport type surfaces, and also possibly unique. That was the predictions 1A and 1B. Okay, Eris probably has an atmosphere, again, almost very likely at some point in its orbit, and possibly even today, although it would be, because it's so much colder, it would be a little bit different from that on Triton and Pluto. Again, it probably has very few impact craters, and so is prediction there for a young surface. Um, and then the blue is the endogenic. We've seen tectonic, and there's cryovolcanic hypotheses on all of Triton, Pluto, Charon. And so I think it's, given what we've seen, it's very likely on Eris as well. And Chris talked about earlier in the week, Chris Klein talked about how the D to H ratio suggests that the methane may be sourced from the interior, possibly coming out cryovolcanically. So just going a little bit more into the atmosphere and the volatile transport on Eris. We have predicted that Eris, because it's so cold, is in an atmospheric regime where you have the sunlight sublimating the volatiles off the surface, just like on Triton and Pluto. It's enough volatile that this is not, say, an exosphere where each molecule takes a ballistic trajectory and then crashing the surface. They're collisional. There's relatively high pressures in that sense that the particles are way more likely to collide than to have a ballistic trajectory. But because it's so cold, it's localized basically to the spot on Eris where the sun is keeping it warmest, and then as you move away from that spot, it's quickly freezing onto the surface. So that's what is meant here by this local atmosphere. And so I have, with others, produced a model that looks at the thermal evolution of the surface and as well as the volatile transport for this type of atmosphere. It's a model that has 4 equations and then 4 variables. And then when we run that model for Eris, what we find is there is a significant amount of volatile transport on Eris today for the assumptions that we made. Most important that I think may not be may be time to revise is the albedo was assumed to be lower, and so that very high albedo may reduce this. But nevertheless, we predict significant volatile transport, where by significant here, of course, that's relevant. But if you were to take, say, one Triton or one Pluto atmosphere and condense it onto the surface as ice, you get roughly the same amount of ice. You can move that amount of ice in roughly an Earth year to 10 Earth years around the surface on Eris, which is long, by our time scales, but is very short on an Eris orbit of many hundreds of years. And so you can really change the surface that we see, and over longer time scales, you can really sculpt the surface with that. So I think this is probably affecting the surface, and it is what I would consider significant volatile transport on Eris. All right, so switching to Haumea. Haumea has been introduced. Of course, it is a very interesting place with this very, very fast rotation. Has rings, it has moons. Its visible albedo is similar to that of Charon. Again, high relative to most worlds, but much less than, say, Eris or Triton or the bright areas of Pluto. It does have at least one albedo feature. The rotation, the variation in the rotation suggests that there's a dark and red area, maybe a spot, maybe larger province, but at least some variation in albedo. The color again is kind of like Charon; it's roughly neutral with a red area. And then no volatiles have yet been seen, and probably will not be seen on Haumea, but refractory materials. So topography, there is of course this very unusual shape of a traxial ellipsoid. It's not at all spherical. And then as far as topography, there's at least one prediction literature for topography of an equatorial ridge. The idea being that if that ring was accreted onto the surface, it could form a ridge around the equator, and perhaps something similar to the ridge that has been seen on Saturn's moon, Iapetus. And then as far as age, I put a question mark there. There's, as Noemi talked about this morning, there's been suggestions in the literature that the age is young, given the crystalline water ice, but Charon's surface is crystalline as well. and has an old crater retention age. And so I personally, I suspect that Haumea's surface is probably quite old. So it's interesting to point out when thinking about landforms on Haumea that because of this very, very fast rotation, the effective acceleration at the surface can vary between the pole and equator by potentially up to 2 orders of magnitude or even more than 2 orders of magnitude. And so there's a paper that's been submitted that suggests that this could actually result in different morphologies of impact craters. And so it's kind of interesting to think about, what would an impact look like in, say, a low gravity environment, but perhaps on a large world where it's, consolidated materials. And then while I was putting this together, I was thinking about, these objects in the inner solar system that we've seen that do have very fast rotation periods. They are, their surfaces are being changed by their very fast rotations. And they're being changed, I think, in both an endogenic and exogenic way. So on the left here is Dinkinesh, where you have this huge area that Hal Levison likes to say, kind of in a plate tectonic sense, like it looks like it would fit back onto the surface as being broken apart. And so that's probably because of the fast rotation is wanting that to split apart. And so Haumea, with its very fast rotation, perhaps we would see something like this kind of tectonism of affecting the surface in that way. Bennu is a little bit different. Bennu is more like a regolith where it's moving along the surface because of this rotation, and that's changing the surface. And so if there is a regolith, maybe an icy regolith, these are of course are rocky worlds, but Haumea is an icy world, maybe an icy regolith could have this type of effect. And so I think potentially we could see either tectonic, endogenic, or regolith, maybe externally produced, so exogenic variations in landforms because of this very fast rotation on Haumea. Could be something interesting. All right, so that brings me to my conclusion in the last slide. So I just want to say again that all three of Triton, Pluto, and Charon each have remarkably diverse, unique, and active surfaces. And they're diverse, again, within their surface and between each other. And that's due to primarily endogenic and exogenic landforms. And I think that all of these attributes are probably true of the areas that we haven't seen on Triton, on Pluto, and Charon, and also these trans-Neptunian worlds that we haven't yet seen as well. So I think those are exciting predictions, but then, what specific exact landforms I think is actually much more challenging for those worlds. So I'll stop there and thank you.
All right. And just like a pro, we've got time for questions. Well done, Jason. Go ahead, Will.
That's really cool thinking about the difference in gravity. I hadn't thought of that before. But what popped into my head when you were saying that was thinking about cryovolcanism and the difficulty of getting a melt to the surface. In a low gravity environment, you need a lot less pressure from like gas coming out of solution or whatever to get magmas to the surface. Very cool idea.
I like it.
Jason, great talk. Thank you for putting it together. Just two observations. The first is that the diversity that we're seeing in these icy dwarf planets, I think, means that the worlds of the Kuiper Belt rival the diversity of the terrestrial planets. And I think that's a very important change in our thinking.
Yeah.
Because we initially expected a lot of the same, and we're seeing nothing but diversity, everything from satellite populations,
yeah,
all the photometry, colors, compositions, atmospheres, surface features that you're talking about. Second observation is to be a little careful, and I'm speaking to everyone, not just to you, with regard to Triton and Pluto, at least, in that we know that with this extreme volatile transport that they see, and a very highly variable volatile transport with time, that we're only seeing a single frame in each of those two movies.
Yeah.
And that they probably look very different at different times.
Yeah.
And so making broad conclusions about whether one world does or doesn't have certain type of phenomena might be biased by the fact that we're limited to just this little slice of time out of all these many types of forcings that are taking place on orbital timescales, seasonal timescales, Milankovitch type timescales. And if anything, we should broaden our thinking, I think.
Thanks for both comments. Yeah, appreciate that. And I fully agree.
Jeff Mornes Ames, great talk. I was going to make one comment. You showed a picture of Triton, you labeled features on it, and you pointed out the southern hemisphere as a polar cap, and it's a common misconception which actually goes all the way back to pre-encounter notions of what people thought they would see. And in the spirit of what Alan was just saying, that we should bear in mind that when we look at these worlds, we shouldn't take our terrestrial prejudices forward, and you see a place that has a bright hemisphere which extends all the way to the equator, we should acknowledge that as an unusual feature in itself.
I agree. Thanks for pointing that out, Jeff. Yeah. In my defense, I did put a question mark on there.
Okay.
But I agree with you. And in the paper, I called it the Southern Hemisphere terrains. But yet your point is we have time, so I'll just say I agree with you. See, there's my question mark.
Okay.
I agree with you, and I think that's whether or not that is a volatile polar type cap or not, I think can tell us a lot about, first of all, those plumes, and just be a first starter in understanding Triton surface.
Well, it certainly has volatiles on it, or we wouldn't see the plumes. So that in itself is a given, I think. But it's interesting that you have this weird dichotomous world where, best we can tell, if you go back to the previous slide, you can't see very far north beyond the terminator, but you can see that white line running east-west is the equator here, and it pretty much demonstrates that, at least to the limit we can see, the surface of Triton. It has a bright southern hemisphere and a dark northern hemisphere, which is interesting in its own right.
Yeah. Thanks, Jeff.
All right, sure.
Guess I'll go next. Wonderful talk, Jason. I'm struck by the 99% albedo on Eris. If you could go to that slide. If you have that high an albedo, you've got very little solar energy coming in. So is it likely that Eris is in a snowball Earth kind of situation? Also,
Say that
it's a
first.
snowball Earth. Basically,
Oh, snowball.
you've got and that much albedo. Also, you don't have much room to have anything that's variegated or dark. It's basically just uniformly bright. So I'm wondering, this is sort of a theme with what Alan was saying, is when we were seeing Eris during a very cold snowball-like era in its evolution.
Yeah, I find that I still scratch my head about that. I didn't have, I didn't put it on because of room on the PowerPoint, but there is an uncertainty on there. So that could come down, say, to more like 90%. I wouldn't be surprised to see it come down a little bit, personally, but I agree with you. Either way, it's extremely high, and it could imply, very low surface temperature. And so that could negate some of this predictions for volatile transport, unless the emissivity is also very low, which could happen because if you're a very bad absorber, you're not a very good emitter either. And so that could help reduce that effect.
And hearkening back to James Keen's and Will Grundy's talks earlier this week, where they were showing you the energy budgets. Remember, the solar insulation was by far the big elephant in the room, and you've knocked it way down for Eris. So it's going to be a very interesting world.
But yeah, it's an extremely high number, and so to put it differently, it could reduce our predictions of volatile transport, but I think it increases our predictions of diversity because I don't think we've ever seen a surface like that. Even the snowiest surfaces on Earth are not like that, right? Right. So what does that mean?
Thank you.
Yeah.
Jason, a couple of questions regarding the bright features you're showing in Sputnik Planitia. I was wondering, you showed just one specific location. Do you see such features at other locations, for instance, in nitrogen ponding outside Sputnik? And does the feature aligns well with surface features such as pits or dark
Yeah.
area, or things like that?
Those are great questions, Tanguy. Yes, we see others. They're not as big or quite as dramatic as these. These three are picked because they are the most photogenic, but we do see about 30 And that's limited by the high phase angle observations because the high phases are crescent images. We don't have huge coverage of them, right? So we don't see a lot of the area, but we see them all. They kind of are located along this eastern boundary of Sputnik, all 30 of them that we see. So that's where they are. And not all of them, but some of them do either conform to like the topography here or to the pits, like you said. So that's what makes me think they're more likely surface features, but it's worth pointing out that these are very thin features. And so if you say, imagine a cloud over the surface and over a pit, you might not even recognize it over the pit because that change in the image is going to swamp what you would see from that feature. So I think they still could be atmospheric, but I prefer surface. And yeah, I'm happy to send you the preprint so you can see more about it.
Okay, thanks.
Yeah.
Hi, Jason, Kirby Runyon, PSI. I was really interested with your comment of the gravity gradient on planets like Haumea, thinking that it might change so much. And and it's okay if you don't have like a coherent answer to this, but something to at least be cool to think about is what experiments, what might you design for cratering and ejecta emplacement, maybe in a reduced gravity environment, to look at the geomorphology effects and any of the process differences that reduced gravity or even gravity gradients might play in that, and what you might expect to see.
Right.
Yeah.
Yeah. Well, I encourage you to take a look at that paper for sure.
All right, which paper?
The one that's so the reduced gravity, the variation in gravity was pointed out by, not by me, but by sorry, where did there we go, by McDonald and Oha, and it's on the archive. So that's worth taking a look at. The thought that comes to mind when you said that is a cool experiment, I think, would be in low gravity, if you have a solid ice consolidated surface versus one that's powdery, how does that change your, say, impact morphology? Because we've seen maybe a place like Arikoth that has very low gravity in ice and a low density. But Haumea is this huge object, and so maybe it has that low gravity, but the surface is much more, like a Karen style, like lithosphere, and so maybe it could be different from Arikoth. That's what comes to mind.
Hi, Paul Shank again. Great stuff. This is more for all the speakers today, philosophically. I too have also been struck, as we all I think are, by the great diversity of composition and dynamics and geology as well. But I'm wondering if there is any kind of unifying aspect to these bodies that sort of ties all this diversity together. And I think maybe the density plot from the previous speaker might go partway to answering that, but it's just something perhaps to give some thought to.
Interesting point, yeah. I don't know
Hey, Jason. Cool. I just was marveling at, of course, when we've had this conversation before about, the albedo being 99% and so forth, and maybe 0.99. And I just worked out that number. We talked about this before, but that would mean that the surface temperature is about 18 Kelvin in a situation like that.
depending on the emissivity. Anne's shaking her head behind you, so maybe she should, that number comes from Anne.
Yeah, okay, but I just wanted to, comparatively, if we take, as a guide, you take Pluto's geothermal flux coming to the surface, that also comes out to about 17 Kelvin, which is kind of an interesting regime as well when we think about boundary conditions and the date near the surface. So it's pretty wild. I mean, that joint. And so we need to, wherever Will is, where is he? Here, wait. Okay. But we have to just revisit this problem that we've been kicking around and pull it out of the drawer. Yeah. Yeah.
Yeah.
Anyways.
That's an interesting point.
You go too far? Real fast, somebody may already be done. We talked to John Stansbury. Somebody needs to get a thermal infrared measurement of Eris to see whether it really is 18K. I mean, a perfectly reasonable calculation you did, but it's also a rather bold one, and it's easily tested. I don't disagree with you. Oh, yeah, you go way down, but go ahead. Go ahead.
The new albedo, what is it?
And Frobisher, UVA. Yes, the bond albedo of Eris is very high. However, we have a new paper out that has been revised, came out in June, where the phase integrals and bond albedos for all the dwarf planets have been revisited, recalculated, and for Eris, the new number is 0.93. So it's still high,
Okay.
but the upper limit is now 0.99 on that. So and also have much better error estimates on everything. So
Great.
it's, yes, still extremely high. I don't know if that will raise the temperature that much above 18K, but
Thanks,
not
Ed.
quite the point, quite the 0.99.
Yeah.
And, I stood up and then I sat down because I thought Will just said it all, but, sorry, Leslie Young, Southwest Research Institute. So the important thing about radiogenic heating is that it sets, you can't get colder than, even as you leave the sun, even as you get very bright, even as you're in an Arctic night. So for Eris, definitely, but even for Pluto, we have to keep those in mind.
Thanks, Leslie.
All right, I think that's all we have time for. So if we could thank Jason one more time.